In the warm-up, you were asked to find the horizontal asymptotes of functions that looked like this. So I took two of the functions from your warm-up, and they want us to rewrite them in limit notation. So what that means is we're seeing like, can we rewrite this with the limit in the front? So we've got limit of this function, and today is all about the limit as x goes to infinity. So if I did the limit as x goes to infinity of this function, think about when you have a horizontal asymptote. So in the warm-up, hopefully you saw the horizontal asymptote of this function is at 2/3 because the degrees match. So at 2/3, I've got this horizontal asymptote. So as x is getting bigger and bigger and bigger, your function is probably going to be approaching that horizontal asymptote. So as x goes to infinity, your function is going to be getting closer and closer, either from above or from below, to that horizontal asymptote. So the horizontal asymptote is actually going to be your limit as x goes to infinity for this rational function. Same thing on this one. If I did limit as x goes to infinity, hopefully from the warm-up, you looked at this and you compared the two degrees. So you had a 4 and a 5. So the 5 was bigger. So you knew when the degree is bigger on the bottom than the top, the horizontal asymptote's at 0. So that means when I'm thinking about my graph, my horizontal asymptote's here at 0, so your function's getting really close to 0. So as x goes to infinity, the y value you're getting close to is 0. So formally, a way you could say that is if you have some rational expression, px over qx, and then the rational function looks something like this, where n is the degree of the polynomial in the numerator and m is the degree of the polynomial in the denominator. So it's talking about this is the n, this is the m. So if n is less than m, then your limit's going to go to 0. So basically, if the degree on the bottom is bigger, your limit is going to go to 0. If n equals m, so if your two exponents are the same, you're going to divide the leading coefficients. So that's what this is saying. And then if n is greater than m as x goes to infinity, that's if the degree is greater on the top than on the bottom. That's when your function does not exist. So if the degree is greater on the top. So the first time I saw that was just a lot of mathy looking words for me. So I wrote it in a way that makes more sense to me. So to me, this is the way that I kind of think about it. This is an example. If the degree is greater on the bottom, it converges to 0, or like the limit goes to 0. The degrees match. So if they're the same, it converges to 3/2 for this one because we have 3/2 in the front. So it's the leading coefficients. So this one, the limit goes to 3/2. And if the degree is greater on the top, the limit does not exist. So whichever way makes more sense to you, you're just thinking about the degrees, and that helps tell you for these rational functions what the limit as x goes to infinity does. So 4 quick examples. Here the degrees match. It's the limit as x goes to infinity. So you're wondering the horizontal asymptote, so you just take the two leading coefficients, so your answer is 2/3. On this one, still x goes to infinity, so we're going to compare our greatest exponents. So on the top it's a 10, the bottom it's a 20. So it's greater on the bottom, so it's going to converge to 0. This is a tricky type. So when you have a square root on top of an x squared, we're actually going to think about, okay, what is square root of x squared? That's going to be an x. So we're considering these degrees to be the same. So I'm thinking about this is an x to the 1 and this is an x to the 1. So because our degrees are the same, we're going to take the leading coefficients. So the leading coefficient on the top is the square root of 2, and the leading coefficient on the bottom is 3. Finally, we have a degree greater on the top than on the bottom, so this limit is not going to exist. So why don't you guys go try out finding some limits as x goes to infinity on some rational functions.